acid-base balance. So as I've mentioned, your body is going to work to control the pH. So we have terms for if your body is slightly acidic or slightly basic. So things like alkalosis or alkalemia. These are terms that are used when your arterial blood pH goes above 7.45. So if it's 7.4, it's normal. Because blood's range is 7.35 to 7.45, slightly basic. So if it goes above 7.45, alkalosis. If it goes below 7.35, this is called acidosis or acidemia. This is also sometimes referred to as physiological acidosis, which we will talk about when we get into the cardiovascular and respiratory systems. All right, so where do we get these hydrogen ions to make things more acidic? Most of them are going to come from cellular metabolism. So the breakdown of a glucose molecule into energy. So a couple of examples here. We have the breakdown of phosphorus-containing proteins. This is going to release phosphoric acid into the extracellular fluid. ECF stands for extracellular fluid. This is the fluid that surrounds the cell. This phosphoric acid is going to have hydrogen ions. It's an acid. Anytime you hear the word acid, it has hydrogen ions. So this acid is going to be able to give up these hydrogen ions to make it, the fluid acidic. If we enter anaerobic respiration is when we are trying to create energy from glucose without the presence of oxygen. So when that happens, glucose is actually converted into lactic acid, which means it can donate hydrogen ions to the tissue that it's in. Fat metabolism, when we break down fatty acids and allow them so that they can go into the energy production cycle, we are going to yield organic acids, ketone bodies, and these are all going to be able to donate hydrogen ions. If we transport carbon dioxide as a bicarbonate ion instead of a CO2 ion, this will also release hydrogen ions. So as you can see, there are a ton of ways that the human body is able to get a hold of substances that will give off hydrogen ions. So how do we regulate this? It depends on the speed. So that buffer system we've already mentioned, that's going to act within seconds to automatically pick up or give off hydrogen ions. A little bit later, after a couple of minutes, our respiratory system is actually we're going to start exhaling excess hydrogen ions or excess bicarbonate ions. So that's within minutes. Our primary acid-base balance mechanism, our renal, takes a couple of days. And the reason for that is, yes, your blood is going to circulate many, many times through your kidneys in a day. We'll talk about that with the urinary system. But it's going to, every time your blood circulates through your body, it has to pick up these excess or get rid of these excess hydrogen ions, depending on where the imbalance is. And then it's got to bring it to the kidneys, and the kidneys have to cycle it through the nephrons, and then it's got to circulate again, and then it's got to circulate through the nephron again, and then it's got to It takes time. So while the kidneys are the ultimate balancer, they do take a while for them to do their thing. All right, so this buffer system. If we have a strong acid, that means that when they are placed in water, the hydrogen ions, all of them, disassociate. So they completely let go of all of their hydrogen. A weak acid only gets rid of some hydrogen ions. So weak acids are great for helping to prevent pH changes. Strong bases are great at helping to maintain pH as well, because strong bases again dissociate easily and quickly will tie up hydrogen. So they'll break apart whatever the molecule is in water and readily tie up any free-floating hydrogen that it can find. So it's going to work quickly and completely. Whereas weak bases they're not going to completely dissociate. So some of them will hold on to some of their hydrogens and some of their other compounds. And so they'll still accept hydrogen, but they're going to do it more slowly. They're not going to be as fast, and they're not going to take up as much. So there are a couple of buffer systems that we use. We use a bicarbonate buffer system, a phosphate buffer system, and a protein buffer system. What is the bicarbonate? Bicarbonate is a mixture of carbonic acid and its salt, sodium bicarbonate, so it's H2CO3 plus NaHCO3. We can also use a sodium or a potassium, which would be a KHCO3, or a magnesium bicarbonate, which would be an MgCO3. We lose the H there. Would be the substance. So if we add a strong acid, such as hydrogen chloride, to a bicarbonate, it will combine with the bicarbonate, because those hydrogens will be picked up, and it will form a carbonic acid, meaning it will form a weak acid. So it will go from a base to a weak acid, and so we will get a slight decrease in pH. So the pH will become slightly more acidic, but if we have more bicarbonate than we have hydrochloric acid, we may not see a bobble really at all, if not much of one anyway. So this is going to be an example of this. This is what happens in the human body all of the time. This is one of the buffer systems found in the blood. If we add a strong base, it will react with the carbonic acid that is hanging out there to form a sodium bicarbonate or a weak base, and we'll get a slight rise in the pH. So it will become slightly more basic. This is a temporary solution. I can override the buffer system by simply adding more hydrochloric acid or more of whatever our strong base is, more than the buffer can actually handle. So I'm going to pick over here. So if I add more hydrochloric acid, then I have bicarbonate ions, I can overwhelm the buffer system, and instead of getting a slight decrease, I can still get a rapid decrease until my respiratory and renal system are able to kick in. Same thing here. If I add more, let's say, bleach, not that you're ingesting bleach, but I'm spacing on a base right now. If you add bleach to this and I add more bleach than I have carbonic acid, I will override the buffer system and it will become not just a little more basic, but a lot more basic. You can overwhelm the system. Phosphate buffer system works basically the same way as the bicarbonate, only instead of our H2CO3 and NaHCO3, we're going to be using H2PO4 and HPO4 2. So one negative charge, two negative charges. One's a slightly weak acid and one's a weak base. Here's the thing. The bicarbonate buffer system, as I mentioned, is going to be important for extracellular fluids, specifically the bloodstream. This phosphate buffer system is going to be used intracellularly, so this is the buffer system that your cells are going to use to stabilize their pH, and this is the buffer system in your urine. Yes, urine has a pH that it wants to be. We'll talk about that when we get there. Then we have the protein buffer system. This is one of the most plentiful and powerful buffer systems. It is found in the plasma, aka bloodstream, as well as inside of cells. So we can find this pretty much everywhere. It's going to use free organic acid groups as well as amino groups, aka amino acids, are going to be utilized to maintain this proper pH, to give up and let go of hydrogen ions. All right, physiological buffer systems. This would be your respiratory system. Its impact on regulating the acid-base balance. It's reversible. So we have carbon dioxide dissolved in water. This is going to form hydrogen ions and bicarbonate ions. Now, these hydrogen ions can leave the bloodstream and be exhaled. So, when we have what we refer to as hypercapnia, hyper, excessive, capno, carbon dioxide, IA, condition, abnormal. So we have abnormally high carbon dioxide, or we just straight up have an increase in hydrogen ions. Your body will automatically work to expel extra or more carbon dioxide. By expelling more carbon dioxide, we take our equation here and shift it more towards the left instead of towards the right, and that will decrease the number of hydrogen ions in the bloodstream, and therefore in the extracellular fluid, and then in the intracellular fluid. So, increase in hydrogen ions will cause rapid, deep breathing. If, however, we're going the opposite direction, we've gone too far to the left of the equation, hydrogen ions have dropped too low, then our breath is going to change in the opposite direction, and we're going to have a decrease in respirations. They're going to be slower, they're going to be more shallow as we shift the equation more towards the right. There's a constant balance back and forth. If we have any issue with the respiratory system, I have asthma, I have chronic bronchitis, I have pneumonia, I have COPD, whatever the case may be, this is going to cause an acid-base imbalance and result in what we refer to as respiratory acidosis or respiratory alkalosis, depending on if it's causing us to be more acidic or more basic with our bloodstream. And this is where the kidneys will then kick in to try and balance that out. They're going to start working on overdrive. So if I have a respiratory disorder and I have a kidney disorder, our blood pHs are shot. This is why when you are looking at a patient, you cannot just look at one thing. You have to look at the entire body, because everything is based on everything else. Everything responds to everything else. We actually haven't talked about it yet, but there's this concept called homeostasis. I like to call it your body's happy place. It's your body's ideal zone of operation, and everything in your body is working to be in that ideal zone of operation. And it is a zone. It has its acceptable highs and its acceptable lows. Anything outside of that is disease, especially if the body is unable to correct itself. So an impact on one system will impact one or more other systems. And if you have the, well, actually, it's not just my physiology class. I think it's all of the physiology classes. I was going to say the pleasure of mine, but I think it's all of them. Actually, we all do this. You will have a paper that you're going to have to do on a disease. And at the end of it, you need to tell us what is the impact that this disease has on other systems. So if it's a respiratory disorder, what other systems are impacted by this respiratory disorder and how and why? Kind of tying it all together. All right, speaking of the kidney, so the lungs are going to eliminate carbonic acid, eliminate carbonic acid by eliminating carbon dioxide. We're going to have chemical buffers to tie up or let go of hydrogen ions, depending on what we need. But the kidneys are the only ones who can actually get rid of them. So if we have too many acids, if we have too many bases, the kidneys are the only ones who can actually get rid of them. They are the ultimate acid-base regulatory organ. So what are some metabolic acids? Things like phosphoric acid, uric acid, lactic acids, ketones. All of those can only be gotten rid of by the kidneys. We do have mechanisms in place that can kind of break down some of these and put them in different formats so that they can be utilized, but those only work so well. If we have too many, we have an excess of ketones, those mechanisms are not going to be able to keep up with that. So this is a regulatory system, the ultimate regulatory system. How does it do that? When the blood is circulating through the nephron can conserve or reabsorb bicarbonates, but it can also make new bicarbonate ions. So it can replenish the buffer system. If we have too many bicarbonates, because remember bicarbonates are a byproduct of that acid-base mechanism, it can also get rid of them. Every time our kidneys excrete a bicarbonate ion, it's basically the equivalent of gaining a hydrogen ion. So every time we get rid of a bicarbonate, we make our blood slightly more acidic. Every time we reabsorb one, we make our blood slightly more basic. And so this is going to be the ultimate mechanism for regulating our blood pH. So if we have an excess, or if pH is too low, so we're too acidic, we're going to excrete excess hydrogen ions, retain bicarbonate. And if pH is too basic or high, we're going to do the opposite. Retain hydrogen, excrete bicarbonate. Okay, so for my respiratory specialist, this is a slide that you are going to want to keep a hold of. Respiratory acidosis and alkalosis. These are going to be a result of a failure of the respiratory system, as we've mentioned. Well, what's being measured here? We're measuring the CO2 pressure. That PCO2 here, right here, that is the pressure of CO2 in your lungs. Normal is going to be somewhere between 35 to 45 millimeters of mercury. millimeters, Hg, mercury. Hopefully you recognize this already from blood pressure. This is how we measure pressure in science, especially in the human body. Millimeters of mercury. We have a couple other things for other types of sciences, but for medicine, Anything medically related, millimeters of mercury is what we use. All right, so between 35 and 45. If that value goes above 45, that's respiratory acidosis. If it's below, it's respiratory alkalosis. So when you're doing your measurements, this is what you're paying attention to. You want to pay attention to these numbers right here. Now here's the thing. Respiratory acidosis is the most common. We don't see respiratory alkalosis as much. Respiratory alkalosis tends to be very short-lived and fleeting because respiratory alkalosis is due to hyperventilating. So panic, fear, you did too much, you ran too fast, too quickly. Like you were running a 5K and you saw the finish line and you're like, you're dying, but gosh darn it, you are going to sprint towards the finish line anyway. Short term, you recovered. Respiratory acidosis, though, this is when a person breathes shallow or we have an exchange of gas that's hampered. So this is pretty much every single respiratory disease. Almost every single respiratory disease is going to hamper the gas exchange and or cause a decrease in the amount of air that can be brought into the lungs. Pneumonia, cystic fibrosis, emphysema, asthma, chronic bronchitis, COPD, CHF, which is actually a cardiac condition, can cause respiratory acidosis because of what CHF does. Metabolic acidosis, though, this is going to be the second most common cause of acid-base imbalance, and this is going to be due to abnormal carbon dioxide levels, but more specifically the bicarbonate portion of that equation. So if the bicarbonate ions are above or below 22 to 26, then we have an imbalance. The acidosis is the second most common and typically due to drinking too much. Okay, that's the most frequently known reason in people who are otherwise young and healthy. Other reasons could be an accumulation of lactic acid. You've worked out too hard. Okay, there's an actual thing, it's called rhabdomyolysis, in which your muscle cells self-destruct, releasing into your bloodstream a slew of compounds and molecules that overwhelms your kidneys, including lactic acid. This would cause metabolic acidosis, but far more concerned, it's going to overwhelm your kidneys and it's going to cause your kidneys to shut down. Rhabdomyolysis can kill you. It can also just destroy your kidneys and have you on dialysis for the rest of your life at the age of 25 or 21, or whenever it happens. There is such a thing as too much pain, no gain. You know that saying, no pain, no gain? Yeah, toss that right out the window. If you are unable to walk after your workout, you did too much. If you cannot walk the next day, you did too much. If you go to the bathroom after working out and you are peeing like a dark brown, almost Coca-Cola colored urine, you check yourself into the hospital. That is like one of the number one signs of rhabdomyolysis. Anywho, sorry, got sidetracked. Other reasons for metabolic acidosis, well, kidney failure, shock. You've had a huge shock to the system. Ketosis, if you're in a diabetic crisis. Starvation. All of these can cause a metabolic imbalance. Alkalosis, this is going to be rising blood pH and bicarbonate levels. This is going to be due to things like you've had the flu and you've been vomiting nonstop for a couple of days. or even 24 hours, really. So anytime you're vomiting up the contents of your stomach, that's going to send you into metabolic alkalosis. Short term, hopefully it's not a chronic condition, but this is partially why even things like eating disorders like bulimia, beyond their mental effects, beyond the effects that constant vomiting is going to have on your esophagus and your teeth, it's going to have long-term ramifications for the rest of your body as well. Bulimia tends to get like it's not that bad. I mean, it's not anorexia. And I guess in a degree of orders, sure, bulimia is not nearly as bad as anorexia. But it's still bad. All eating disorders are bad. We have actually, if you or someone you know suffers from an eating disorder, we have mental health services here on campus. They're located right in our learning center. Go and talk to them. Just having someone to listen can be a huge benefit, and non-judgmental listening. I mean, from a healthcare side, I will definitely listen, but I'd be urging you to seek a nutritionist's help, because you're going to need to start correcting the imbalances you have created. And hopefully, you've started to correct it early enough, but these diseases can have long-lasting ramifications. So seek help. It is not too late, and you're not alone. Sorry, I got sidetracked again. The other way we can have metabolic alkalosis is excessive intakes of bases. So you're popping antacids left, right, and center. That's a problem. All right. So, as I've already mentioned, if one system is unable to maintain its physiological buffer, the other one is going to kick in and try and correct it. So if my respiratory system is off, then my kidneys will try and correct. If my kidneys are off, my respiration will try and correct. And it would look something like this. Metabolic acidosis, your rate and depth of breathing are going to elevate because your blood pH is below 7.35. This is going to increase your PCO3, but as we increase our rate and depth of breathing, this is going to cause your PCO3 to fall below normal. So this will there'll be the strange little time frame where your body's like, okay, do I still want to do this? Because now this system is off. This is that cascade effect. In metabolic alkalosis, so we're over 7.45, we're going to institute slow, shallow breathing. This is going to cause your PCO2 to rise above normal because we're going to start to retain carbon dioxide. And the hope is that by doing this, we'll be able to flip on a different mechanism. And the renal, same thing, only just from the kidney side.